Okay, conservation of momentum is something that you probably would have learned under IGCSE before, right? So momentum, is the product of mass times velocity. It is something that an object that moves will always have. Okay, so most of the time when you're talking about moving objects, they will normally move and then they will hit something else. A not moving object won't move indefinitely to infinity. Eventually, something will be in its path and then will collide with that object. Okay, so what we're interested to know is what happens when an object collides with another object. Okay, so specifically, when an object collides with another object, we have something called principle of conservation of momentum, which states that the sum of momentum before a collision is equal to the sum of momentum after the collision in an isolated or closed system. In your definition for exams, it is important to always use this sum of momentum equal to sum momentum before collision is equals to sum of momentum after collision. If you do not have these two words, normally they will subtract off your answer. They will deduct marks. Okay. You cannot say it's momentum before collision equals to momentum after collision. That's not precise enough. You must say sum of momentum before collision is equal to sum of momentum after collision, provided that it is a closed or isolated system. Okay, this is the other keyword here. Now, what is a closed or isolated system? A closed or isolated system simply means that the system has no other external force acting on it, such as friction or air resistance. Okay. If total momentum is conserved, the total momentum of the system remains constant. There's no change in momentum of the system. However, the individual objects in the system will experience a change in momentum. Okay, now what is this one talking about? So let's just go through a few of the examples. All right, what do I mean by that? Okay, now maybe I just use these three as the example. Clear this one off. Okay, what do I mean by this? Now, when it comes to collisions, there are a few cases that can happen. Let me just give you a few examples of collision. Example collisions. It could be that maybe you have object that moves like this, and then it hits a stationary object. And then after that, what happens is that this object stops, and then this object starts to move. This is example one. Another one could be that this object moves here, same as before, hitting the stationary object. And then after hitting the object, both of them start to move. And then the third case could be that this object moves. Again, it hits a stationary object. And then after that, maybe what happens is that this one moves towards the left, this one moves towards the right. And then the last one could be that maybe the object was same thing again, going towards a stationary object. And then once it hits the other object, both of them stick together and move as one. Okay, so these are some example collisions that you can think of. All right. So when we say sum of momentum before collision is equals to sum of momentum after collision, it just simply means this. The sum of the initial momentum here must be equal to the sum of the final momentum here. Say, for example, if I tell you that this one is, say, 20 Newton second, this one is 0. This one, the sum of initial momentum is 0, right? As the sum of initial momentum is just going to be 20. According to conservation of momentum, the total momentum after collision must be the same. So if this one here is already at 20, the final momentum, total final momentum must also be 20. So in my case here, this one here must be 20 Newton per second, while this one is 0. Okay, that's what conservation momentum means. The total momentum before after collision is the same. Maybe this one I write it a bit up here. This one must be 20. This one must be 20. Okay, so the same will also go for the second example. If I tell you that the sum of initial momentum must be equal to the sum of the final momentum, the total momentum must be conserved before and after collision. If this one is 20 Newton second and this one is 0, so initial momentum is 20. And then this one here, you see, both objects are moving. So, but the thing is that the sum of the final momentum must be the same as the sum of the initial momentum. Since the sum of the initial momentum is 20, the sum of the final momentum must also be 20. So in my case here, what I could possibly have is that maybe this one is going to be 12 Newton second, and then this one is going to be 8 Newton second. So these two add up together will give me back 20. Okay, so here just now in the fourth statement, I said that if momentum is conserved, the total momentum of the system remains constant. There's no change in momentum of the system. It's actually referring to this. Okay, all right. When momentum is conserved, total momentum remains constant. There's no change. You see over here, before collision is 20. After collision is still 20. There's basically no change from here to here. What I mean is that if I talk about between here and here, the change in momentum is actually 0. Okay? So when we say something is conserved, it can mean one of two things. The value remains the same. So if the value remains the same, there's no change. Okay, they are all indirectly mean conserved. Okay, so in my case, if I say the momentum is conserved, total momentum of the system remains the same. There's actually no change in momentum of the system. Okay, but over here, I said that the individual objects in the system will experience changes in momentum. So if I look at the second example, this one here, you will see that the momentum is still conserved before and after collision. The change in momentum is actually 0. But what I want you to see is the momentum of the individual objects. You see, the system here consists of two objects, right? This first sphere and the second sphere. All right. Now, if you look at the first sphere, it originally had a momentum of 20 Newton second. But after the collision, the momentum has actually changed from 20 Newton second to 12 Newton second. And then if you look at the second sphere, originally the momentum is 0. After collision, it suddenly had a momentum of 8 Newton second. It actually had a change in momentum. So what you can see here is that the 20 Newton second changed to 12 Newton second. The 0 changed to 8 Newton second. This is actually what this statement is trying to tell you. If you're talking about individual objects inside the system, they can have momentum change. But if you're talking about the system itself, the whole thing all added together, the momentum, total momentum will not change. Okay, so that time I also mentioned that your momentum before and after collision will be the same provided it's an isolated or closed system, right? So when we say something is isolated or closed system, it just simply means no external force, no friction or air resistance acting on it. So like for example, this case here, if I talk about the first example here, which was this one, okay, if you suddenly have friction, let's just say right now the first example here, this one, there is no other force indicated during the collision. This is considered to be a closed or isolated system. But if, say, for example, right now, I tell you that there is friction here, okay, friction acting when the two objects are colliding, then this is not a closed system. Okay, if I suddenly have friction acting when the two objects collide, this is not a closed system. Okay, a closed system is only closed when there's no forces acting on the system. Okay, like in my case here, if I suddenly have friction acting when the objects were colliding, this is not a closed system. For it to be a closed system, there must not be any external force acting. Okay, now when this object collide with this, they will exert forces on each other. That one is okay. That is force. It's within the system itself. What we do not want is a force that acts on the system, external force acting on the system. Okay, so if I talk about the third and fourth example here, we can still talk about the same thing. If this one is 20 Newton second, this one is 0, the sum of initial momentum before and after collision must still be the same. Sum of PI must be equals to the sum of PF. Okay, I here stands for initial, F here stands for final. So if here right now the initial momentum, total initial momentum is 20, the sum of the final momentum must also be 20. Okay, but now here you have momentum in opposite directions. This one is going towards the left, this one is going towards the right. So what can probably happen is that maybe this one is going to be, say, 28 Newton second. Sorry, let me just draw it better. Maybe this one is going to be 28 Newton second, and then this one is going to be 8 Newton second. Remember that momentum is a vector. It has direction. So when you want to add them up, the ones that is acting in the opposite direction would always be a negative. So right now, because this one is opposite direction,
well,
sorry.
How come it's 8 and 28? Shouldn't it add up to 20 also?
Yeah, it should add up to 20. Because you see, this one is momentum 28 Newton second, 28 Newton second
Okay,
going towards the right.
Yeah,
But this one is 8 Newton second going towards the left, right?
Right,
So in my case, the momentum here would actually be 28 plus negative 8, giving me 20 Newton second.
Right,
Okay?
right. I didn't see the arrow.
Okay. Yeah, okay. So this one is acting in the opposite direction, that's all. Okay. So this one, they will still give you the same momentum after. All right. So this one, again, you see the momentum of the individual objects did change. Okay, change again. All right. Okay, the last one is same thing again, an object that moves towards a stationary object. This one will be 20 Newton second. This one is 0. Now, after collision, this one definitely must be 20 Newton second also as a whole. Okay, this one is now one single object because they are combined together. Over here, I will say that sum of initial momentum must be the same as the sum of the final momentum. This one must be 20. This one must also be 20. Okay, so this is some relations that you are expected to see. Okay, so that is conservation of momentum. Okay, and then now we go more specific to types of collision. When it comes to types of collision, the most important one that you will learn a lot and you'll see a lot inside your exam question is something called elastic collision. Okay, now elastic collision, one of the characteristics is that it will always separate after collision, and then there are two main characteristics. The one that's most important about elastic collision is these two main characteristics. Okay, what we will tell you is that for an elastic collision, total kinetic energy will always be conserved. Okay, so when it means total kinetic energy is conserved, that means total KE before and after collision is the same. Okay, that's why I wrote it here like this. The sum of initial KE is the same as the sum of final KE. Total KE before and after collision is the same. Indirectly, this also means the change in KE is 0. If I say that the sum of initial KE originally was 100 joules, after collision, I expect to still see 100 joules. If they were not conserved, it could be that maybe sum of initial KE was 100 joules here, and then after that, the sum of final KE maybe is 80 joules now. Now, this and this are not the same value. The KE is not conserved. Okay, this is KE not conserved. There is a change in the KE value. This one is worth 20 joules, right? Okay. So strictly speaking, whenever we say something is conserved, I mentioned to you before, the value before and after is the same. That indirectly also means there's no change. Okay, sometimes the wording that they use in the exam questions, they might sometimes say there's no change in the value or the value remains constant. It actually implies conservation of the value. All right, so total KE here is conserved. Total initial KE is the same as total final KE. There's no change in the KE value at all. This is the first important characteristics of elastic collision. Okay, then after that, there's another characteristic of elastic collision where we tell you relative speed of approach is equal to the relative speed of separation. Okay, the relative speed or approach and separation, specifically what is relative speed, this one I'll leave it for the next page, but for now it's just important to know that elastic collision always has these two. Okay, the rest of the collisions that you see in the tables here will not have these two. Okay, whenever we tell you something is having an elastic collision, they must have these two conditions satisfied. The rest of the collisions here do not satisfy this. Okay, now, and also I would also like to highlight to you that the different collisions, the 4 different collisions that you see in the table, all have conservation of momentum. Okay, so in your case here, because we assume that all the systems are closed system, isolated system, momentum must be conserved. Okay, so basically what you're seeing here for the expressions is all talking about the sum of the initial momentum equals to the sum of the final momentum. Okay, and then this little statement here below it, this one is actually talking about conservation of kinetic energy. Okay, COM stands for conservation of momentum. COKE stands for conservation of kinetic energy. So when I talk about the conservation of kinetic energy, I want to get the sum of initial KE. This one will be half m1u1 square plus half m2u2 square equals to the sum of the final KE, half m1v1 square plus half m2v2 square. Okay, and then approach speed equals to separation speed is given by this expression. How you get this, I will explain in the next page. But this one, just remember this one first. Elastic collision, the first two conditions. Okay, then the next one will be inelastic collision. So inelastic collisions, normally they would separate after collision. Okay, they will normally separate after collision. KE is not conserved here. Your KE loss is actually dissipated into heat or sound energy. This is actually talking about this. If your collision is inelastic, your KE is not going to be conserved. The KE before collision will not be the same as the KE after collision. Okay. you will have some difference in value. Normally, you will lose KE, okay? This one here, I did not write this, but maybe you can. Normally, KE after collision, total KE after collision decreases. Okay, the KE before and after is not the same. Normally, the total KE after collision will decrease, like the ones that you see here. Okay, now the difference is actually the amount that has decreased. So that KE that you lost, which is this one is the KE loss, is actually dissipated into heat and sound energies. You see that whenever an object collides with another object, you will hear some sound when they bang together. You will notice that maybe the material, the two objects, when they bang each other, they might deform, right? Or also when they bang each other, there's some heat generated, there's some sparks flying. So that KE that you lost during collision can be converted into other forms, like deforming the object into heat or into sound or sometimes into light. Okay, that's why here we say that the KE loss is dissipated into some other forms of energy, either heat or sound or some other forms. Okay, so this is inelastic collision. Now, the second last one is what you call as perfectly inelastic collision. Okay, what is perfectly inelastic collision? You notice that what's different between the second and third one is that there's the word perfectly. This one is inelastic collision only. This one is perfectly inelastic. Sorry, you can't see it properly here. This is perfectly inelastic collision. Between this one, the second one, and the third example, the only difference between those two is that there's the word perfectly here, right? Okay, between perfectly inelastic collision and inelastic collision, the main difference between those two is that in a perfectly inelastic collision, the particles will always stick together. Okay, so when you hear mention of perfectly inelastic inside your question, just know that they normally will tend to stick together. Here the example is that mass M1 hits mass M2, and after the collision, they both move off together as one. They stick together. They move off together as one with the same velocity. Okay, so the only difference between perfectly inelastic and inelastic itself is just the fact that perfectly will always have the objects sticking together. Inelastic only will just have the objects moving separately after collision. Okay, so this is for inelastic. Now you may be wondering if there's a difference between perfectly inelastic and inelastic. Is there a difference then between perfectly elastic collision and just elastic collision? Now sometimes when you do your question, you might hear the term perfectly elastic collision. Now, perfectly elastic collision is actually exactly the same as elastic collision. There's no difference between them. They are same. But when it comes to perfectly inelastic and inelastic collision itself, they are different. There's a difference between them, slight difference. But when it comes to perfectly elastic and elastic collision itself, no difference. They're actually the same. Okay, so that one is the third example here. Again, the third example, momentum is still conserved. So you will say that M1U1 plus M2U2 equals to M1 plus M2 times V, which is this one here. Okay, this is still conservation of momentum for B. Okay, and then the last one will be this one here. Okay, so the last one, I'll just clear off all the drawings here. It's becoming really messy already. So let me just clear off. Okay, the last one is a case where you're talking about explosion. What we'll tell you now is that a single particle splits into two or more smaller particles. This is what we know as explosion. Okay, so say for example, right now, if this object was stationary, okay, they didn't write here, but it's implied already since I didn't draw any arrow here to indicate velocity. This thing here is stationary. So if this thing here is stationary, the initial momentum is just zero, right? Let me just draw it here. The initial momentum is just zero. According to conservation of momentum, the sum of the final momentum must also be zero. Okay, this one is due to conservation of momentum. Okay, so what we will tell you here is that in general, because your momentum initially is zero, when your objects explode and break off into two different fragments with their own momentum, the momentums of the fragments must cancel each other out. Okay, like you see this one here. This one here obviously has no momentum, but this one has momentum, this one has momentum. This one will be m1v1. This one will be m2v2. You see here, over here, I wrote that m1v1 is the same as m2v2. They are the same with each other. One way of deducing why is it like this is because you know that the initial momentum is zero, the final momentum must also be zero. The only way that your final momentum can still remain at zero is if the momentums cancel off. These two fragments move in opposite directions. So meaning to say one of the momentum is a negative. So they must be equal magnitude in the first place so that they cancel off. Okay. This is one way of deducing why the momentums are equal and opposite. Right. There's a way to prove it mathematically too. This one is the ones that I showed here. Okay, wait, let me just rewrite this one. This one is actually this one here. Let me just show you. You will say that sum of find initial momentum. So initial momentum is same as the sum of final momentum. It's just zero here. This one will be m1 v1 plus negative m2 v2. Okay, maybe I just do it another way. m2 v2 plus negative m1 v1. m2 v2 plus negative m1 v1. Because I remember telling you before that momentum has direction. So when you want to add them out, set something like a sign convention. Which one do you consider as positive? The momentum that's in the direction of your sign convention will be positive. The momentum that's opposite to your sign convention will be negative. So in my case here, this one is in the same direction as my sign convention is positive. This one is in the opposite direction to my sign convention, so it's negative. That's why you get this. Okay. Eventually, you'll get back this result. Look, m1v1 equals to m2v2. You can prove it by just adding up the momentums. All right. But very seldom you'll be asked to prove it mathematically. It's just sufficient for you to know that when your momentum is zero in the first place, if the fragments somehow break up and momentum is to be conserved, meaning to say you want to maintain it at zero, the fragments must have equal opposite momentum. Okay, so this is the last example for collision types. Okay, then the last one would be relative speed. This one I mentioned is in the next page. I did not go through it with you yet. This is where I need to go through with you the concept of relative speed. So I'll just clear off the drawings. So as I mentioned to you, elastic collision will always have total key conserved, and relative speed of approach equals to relative speed of separation. Now, relative speed is just the speed relative to a reference point, which may be stationary or moving. what do we actually mean by that is you can consider something like this. If say, for example, I have person A and then I have person B, this is the first one. I tell you that this person is moving 10 meters per second. This person is also moving 10 meters per second. Now, what is the speed of person A relative to B? The speed of person A relative to B is just 0 meters per second. Because you see, this guy is moving 10 meters per second. This guy is also moving at 10 meters per second. It's as if, from the point of view of person B, person A is not moving at all. It's not moving with any speed. But if I talk to you about another separate observer, person C, that is stationary, the speed of person A relative to C will be that he is moving at 10 meters per second. He's actually seeing the person moving away with a certain speed. But when you're talking about the speed of person A relative to B, is as if that person wasn't moving at all. Okay. A good example of that would be, what I mean by that would be like this now. If let's just say your friend is outside, this is a car, you're sitting inside a car with another friend. So if this one is person A, this one is person B, this one is person C, if you're talking about the same case here, when the car is moving with 10 meters per second, person A is also moving at 10 meters per second, person B is also moving at 10 meters per second. Now the speed of person A relative to B will be that it is 0, because you see, if you're moving, you're sitting inside a car with another friend, all right, and the car moves, when you look at your friend, it doesn't seem like your friend is moving away from you or moving with some speed. It's as if the person is stationary. But if you're talking about person C that's outside the car and standing still, when he looks at the person inside, he perceives that person A and B is moving with 10 meters per second. That is what relative speed is. Okay, it is always the perceived speed, if you would, the speed that is perceived with respect to a reference. Okay, the reference can be stationary or moving. That is relative speed. Okay, so now I give you another example of relative speed. This one I'll just rub it. Okay, another example of relative speed could be, say, same thing as before. Maybe this one, person A, then this one, person B. This time I tell you person A moves with 20 meters per second. Person B moves with 5 meters per second. So the speed of person A relative to B will be 20 minus 5, giving you 15 meters per second. So from the point of view of a stationary observer, C, A is really moving with 20 meters per second. But from the point of view of B, he isn't moving as fast as 20 meters per second because he himself is moving. So he perceives this guy to be moving somewhat slower. Okay, because you're moving at 5 meters per second, this guy is moving at 20 meters per second. This guy here will perceive this guy as moving slower at a slower speed. Okay, there's one example of relative speed. Then another example of relative speed will be this one. Same guy, person A, and then same guy, person B. Now this guy here moves 20 meters per second towards the right, but this guy now moves 5 meters per second towards the left. So in my case here, the relative speed of A to B will be 20 plus 5, giving you 25 meters per second. This time, the speed of person A relative to B seems to be faster because this guy is moving towards the right, this guy is moving towards the left. It seems as if person A is going away faster than B from his point of view. Okay, but again, same thing as before. If you're talking from the point of view of person C, this guy is actually just moving at 20 meters per second itself. So maybe I just write here VA relative to C, it's just really going to be 20 meters per second. And then this one, VA relative to C, it's just going to be 20 meters per second also. Okay, that is what relative speed is. Okay, now this one is just for you to understand the concept. You won't really be asked to explain what it actually is or to illustrate some examples. When you want to find relative speed, the way to find relative speed is written down here. In general, what we'll tell you is that if your objects move in the same direction, relative speed is just simply the higher speed minus the lower speed. Okay, which is actually similar to this. These are two objects moving in the same direction. Relative speed is just taking the higher magnitude minusing the lower magnitude. Okay, so in the example that I have here, if I have object M1 hitting object M2 before collision and then after collision, if U1 is more than U2, the relative speed is just U1 minus U2. If after collision you have V1 and V2 and we tell you that V2 is more than V1, you just take V2 minus V1. Okay. Now there's one thing that and this one is just some trivial thing to know. U1 must definitely be more than U2 because you want to have collision here. If you have 15 meters per second and then this one is 10 meters per second, obviously these objects will collide, right? But what if I shift it around? Rather than this one being 15 meters per second and then this one is 10 meters per second. Now I tell you this one is 10 meters per second and then this one is 15 meters per second. Will the objects ever hit each other? So yeah, will the objects hit each other? If mass M1 is moving at 10 meters per second and mass M2 is moving at 15 meters per second, will they hit each other? Hello?
Oh, sorry, I was muted. Sorry, sir. I was talking, but then you couldn't hear me.
Oh, okay, right, no worries.
I
So
don't think that they were.
cannot, right? So you see,
moving at different speed.
for something to collide with another, one of the object must be moving faster than the other, only then can they collide. So in my case here, U1 definitely must be more than U2, okay, in order for collision to happen in the first place. If one of it was moving slower than the other, collisions definitely cannot occur. All right, so this one, so that collision occurs in the first place, 15 meters per second, 10 meters per second. All right. Now, then after that, why do I say that V2 must be more than V1 after collision? I'm saying now that V2 must be more than V1 is something like this, 8 meters per second. And then this one is maybe 4 meters per second. Now, what happens if I try to switch it around? This one is 8 meters per second. This one is 4 meters per second. If I say that V1 is more than V2, like this, what do you think will happen? Isn't it saying to you that collision will happen again? Right? This one collision happens again. This one is actually not sensible, right? This is not sensible. You normally see that when an object hits another object, the objects either move together away or move separately, right? In the case that they move separately, you don't see a collision happening, then after that a collision happens again, right? It's like you will continuously have multiple collisions. This is just not possible. Okay, so after collision, V2 definitely must be more than V1. So that, sorry, so maybe I use a black color ink to highlight it. This one is so that collision does not reoccur. Okay, collision does not happen again. I'll put it simple because it's not sensible. When something hits an object the first time, giving you the first collision, it doesn't collide again. All right.
Yeah.
All right. So that's why I say that V2 must be more than V1.
What if it's like it hits a wall and then it collides again?
If it hits the wall, say for example, you know, you have a wall. This one it hits, it by right should rebound. Okay, but let's just say you have another wall here, then yeah, it would make sense that it hits this wall, then after that it goes back. But right now I'm talking more about two objects that can move, that have the ability to move. If you're talking about a case where an object hits a wall, it rebounds, and then it hits another wall again, yeah, this one will be a case where the collision keeps occurring again and again and again. That is possible. But the case that I'm talking about now is more like the two objects can move. If the two objects can move, it is not possible that the collision can occur again. All right? All right. Okay, so this is for relative speed when objects are moving in the same direction, where you take the higher speed minus the lower speed. Now, the last one will be what happens if the objects move in opposite directions. Okay. Now, when it comes to objects that are moving in the opposite direction, relative speed is just the higher speed plus the lower speed. When I say that an object moves in opposite direction, it could be something like this. Mass M1 moving towards the right, mass M2 moving towards the left. This is moving in opposite direction. Or mass M1 moving towards the left, mass M2 moving towards the right. They are both considered opposite directions in this case. So relative speed will just be higher speed plus lower speed. U1 plus U2, B2 plus V1. It's actually similar to this case. You see this case, the objects move in opposite direction. Relative speed is just one plus the other. Okay. Now, specifically when you're doing this way of finding relative speed, any object moving in opposite direction does not need to have any negative sign. Okay. Don't need to bother about negative sign. Just consider the magnitude. All right, because I know that before this, you have been considering a lot of the negative sign whenever you see the object moving in opposite directions, especially if it's a vector. For this particular method, don't bother about the negative sign. Just consider magnitude only. Okay, so that is for relative speed of objects moving in opposite directions. Okay, there's some example you can do. This one is in the next few pages, page 10. Just have a look at page 10. There are some examples here that I will do with you before I move on to your past years. Okay, now you have two trolleys X of mass 5 kg, Y of mass 2 kg. They are traveling towards each other as shown. X has a velocity of 3 meters per second, while Y has a velocity of 1 meter per second. They collide and then one moves away towards the right with a velocity of 2 meters per second after collision. Calculate the velocity of trolley X after collision. This is the case before collision. Okay, they want the velocity of trolley X after collision. What they have described to you here is that y will move towards the right with velocity of 2 meters per second after collision. This would mean that y moves in this direction at 2 meters per second. Okay, now that leaves you with only trolley x, whose direction you do not know. Let's just say, for example, right now, you assume that the direction is here. Okay, let's just say for the sake of our discussion, you assume that the direction is in this direction. Okay, to find the velocity here, you always have to use conservation of momentum, which tells you that the sum of initial momentum is equal to the sum of final momentum. Okay, when you read your questions, although they never specifically tell you that the system is isolated or closed, you always assume it is. Okay, it's only when it's assumed to be that way can you apply conservation of momentum. So over here, you apply conservation of momentum, you can just say that m1 u1, oh sorry, this is x, right? I'll just write out the full workings here. This one is just telling you sum of initial momentum is equals to the sum of the final momentum, mx ux plus my uy is equals to my u, sorry, is mx vx minus my vy. Okay, this part here is just for your extra understanding only. In your exams, we don't really require you to write up to this extent. You can actually just start writing the values in. You can probably just write it as 5 times 3 plus, oh yeah, there's a mistake here that I forgot. The negative sign should be for this one, right? This one was moving in this direction. This one was moving in this direction. One of it will have a negative. Let's just say that your sign convention is rightwards positive. So this one is moving opposite. You give it a negative. Okay. And then after that, when you go to before collision, to the case after collision, this one is going to be negative mx vx plus with my vy. This one is going this way. This one is going this way. So this one should have been negative. This one should have been positive. Then this one was positive. This one was negative. Okay, this is how you see this. All right. So like I mentioned, this portion here in the exams, you generally don't need to write this. This is like just me writing the steps from the beginning. It's sufficient if you just start from here. Okay. But be mindful of any negative sign. Okay. So this is 5 plus 3. Negative 2 times 1. Okay, this one I think I better write 5 kg here, 2 kg here. Okay, equals to negative 5 times Vx plus with 2 times with 2. Okay, so from here, you have 15 minus 4, you get 11 equals to negative 5 Vx plus 4. Then after that, you see here, what is your Vx? Your Vx is going to be 11 minus 4 divided by negative 5. You're going to get a Vx of negative 1.4 meter per second. Okay, so what does this negative here mean? This one, the negative sign here would mean that your velocity is actually to the right, opposite to the assumed direction, opposite to the assumed direction in diagram. The diagram, you assume that your Vx was here, right? But right now you're getting a negative. This tells you that your Vx is actually not supposed to be towards the left. It's supposed to be towards the right. Okay, that's what this negative here is telling you. Okay, now if let's just say you didn't assume your direction to be towards the left, maybe you had assumed it to be Vx in this direction. Okay, you can see the working will actually still give you back the same answer, but without the negative sign now. This one I can just reproduce the workings for you. This one is 5 times 3 equals to, sorry, this is 5 times 3 minus 2 times 1 equals to 5Vx plus 4, sorry, plus 2 plus 2. This one will be 5Vx equals to 11 minus 4. Then your Vx will just be equals to 1.4 meter per second. Same answer as before. Okay. But this time you do not have any negative sign. This one is telling you your Vx is actually following your assumed direction here. Okay. So in the event that when you want to determine the speed or velocity, but you do not know what is the direction, just assume one direction. Okay. If you get a positive answer to your final, if you get a positive answer, that means your assumed direction was correct. If you get a negative answer, it just means that the actual velocity is opposite to what you assume. That's all there is to it. Okay. So if you move on to the next part of the question, determine the relative speed of approach and relative speed of separation. This one, you know that x was moving 3 meters per second. Y was moving like this, 1 meter per second. So your relative speed of approach. Now you see, just now I mentioned to you, when you want to find relative speed, you just see whether they're moving in the same direction or opposite directions. This is the case of them moving in opposite directions. If they're moving in opposite directions, you just add up the speed. Don't bother about any negative sign, just add the magnitudes together. So this one would actually be just 3 plus 1, giving you 4 meter per second. And this is relative speed of approach. For relative speed of separation, if you draw out your diagrams again properly, following the correct direction here, this is 1.4 meter per second. This one is 2 meter per second. Okay. Now, in your case here, your relative speed of separation will be slightly different. Okay. This one is the case where they're both moving in the same direction. This one was moving same direction. This one was moving opposite direction. Okay, so in the case where they're moving in the same direction, I mentioned just take the higher speed minus the lower speed. So you just take 2 minus 1.4. It will give you 0.6 meter per second. All right. So this is the relative speed of approach and separation. The next part of the question is asking you, state and explain whether the collision is elastic. Just now I mentioned to you, when a collision is elastic, there are really only two cases, two conditions for something to be elastic. The first one is total KE conserved. The second one was relative speed of approach equals to relative speed of separation. Now, when you compare these two right now, they are not the same, right? You already found the relative speed of approach and relative speed of separation. They are not the same. So you can just say that since relative speed of approach is not the same as relative speed of separation, therefore collision is not elastic. Okay, so this is how you evaluate this question. All right, so this one is okay. Then we move to the next one. This one is also again on collision, but it's more for perfectly inelastic collision. Okay, so if you just move on to the next example, this one should be a short one. You have a sphere of mass m traveling in a straight line with speed 7 meters per second that collides head-on with another sphere of mass 2m moving a speed of 1 meter per second in the same direction. After collisions, the spheres stick together and they continue moving. Determine the new speed. The new speed is this speed. Okay, this one is a case where you see they stick together. This is actually your perfectly inelastic collision because you see that they stick together. All right. So right now you want to find the new speed. You still apply principle of conservation of momentum where you just say that sum of initial momentum is equals to the sum of the final momentum, where you can say that this one is actually m u1 plus m u2. Notice that they're both in the same direction. You can just add them up. And then after that, this one is just going to be m plus 2m. This one is going to be m plus 2m times v. Okay, so you try to sum in the values. This one would just be m times 7. Hey, sorry, I forgot. This one is 2m, right? No mistake. This one is 2m u2. Okay. This one will be 2m times 1. This one will just be 3m v. So the end result is that you have 7m plus 9m, sorry, 7m plus 2m. You get 9m equals to 3mv. Although you do not know the mass, is fine. The mass will cancel off. Eventually, you get the final answer v as 9 divided by 3, giving you 3.0 meter per second. This is one part of your conservation of momentum. Okay, right. This part here, as I mentioned to you, you don't really need to write it inside your workings. It's just a habit that I always write, just to tell you that conservation of momentum is applied here. All right. So if this one is okay, then we move on to some of your past year questions.